Hello, my name is Christine Allen. I'm a data scientist at Kensai Inc., and today I'll be presenting our research into interpretable data phenotyping. Machine learning problems in healthcare are often impeded by something known as the curse of dimensionality. A plethora of data increases our modeling capability, but it also increases the effort required to evaluate those data and generate a model. There are standard featured engineering techniques which can be applied, such as correlation analysis or even manual curation based on the knowledge of a clinician. These work well for problems that are well understood or for problems where the feature space is small. However, using standard techniques, we can easily eliminate important features whose complex interactions are not yet known, or sparse features where certain values are rarely seen, yet make a crucial difference in the predicted outcome. For many problems, there are potentially tens of thousands of possible contributing factors, and this is simply too many to process manually. For these reasons, unsupervised machine learning has become a popular method to automatically extract patterns of related data so that each observation can be described by just a few groups of features, rather than by a larger set of hundreds or thousands. You're probably familiar with the term phenotype from biology class, and you've probably seen a chart much like the one on the left. It demonstrates how a mix of genes can lead to flowers of varying colors. This term phenotype has been co-opted to represent groupings of features in the same way that biological phenotypes represent groupings of genes. There are a number of linear algebraic methods that have been used to address this problem, which fall under the umbrella of unsupervised learning. Non-negative matrix factorization and non-negative tensor factorization in particular are of keen interest because of their success in genetics and biological phenotyping, as well as in other domains. Their difference from standard factorization is that negative values are disallowed. Marble, for example, and its successors use a series of tensor factorization-based approaches to find phenotypes specifically in categorical health data for which it wouldn't make sense to have negative values. Researchers found that their method produced competitively predictive phenotypes deemed to be interpretable by clinical practitioners. And in the Marble paper, at least, they were able to identify at least one novel disease subtype. Significant work has also been put into clustering approaches, particularly k-means clustering and agglomerative clustering, which are already commonly applied in health informatics, for example, to generate patient cohorts in epidemiological studies. Clustering methods group data using one of several typically simple calculations to determine the similarity between two feature vectors, rather. The methods I just mentioned are useful in uncovering novel health states, in detecting specific and well-known diseases, or in population studies. But they're limiting in applications that require transparency and interpretability. And what do I mean by that? Transparency and interpretability are two pillars of responsible machine learning. For a model to have transparency means that a prediction can be linked back to the inputs that generated it. And for a model to be interpretable, one must be able to cogently explain why a given prediction was made. Take the example of a length of stay prediction. If a prolonged length of stay is predicted, it may indicate that a patient is likely to suffer from complications due to comorbidity, which would require medical intervention. On the other hand, it may conversely indicate operational delays due to insufficient staffing or weekend delays, which might require operational changes or possibly require no intervention at all. A transparent model would inform the user that existing comorbidities and operational delays were two factors in the prediction. An interpretable model would inform the user of how those factors relate to each other. In contrast, here's an example output from a non-negative matrix factorization model. We start from a single matrix, which is our input data exemplified on the left, and then we factorize it into two. One matrix associating each patient with each phenotype, and the other associating each phenotype with each feature. In this way, we're able to link the observations to the features through the phenotypes. However, using this system to explain an output is difficult. Looking at the top right table, let's say that feature A indicates a diagnosis like has unspecified anemia. What does it mean that phenotype 3 has 87 thousandths of it? Or looking at the table on the bottom right, what does it mean if patient 2 is 1.24 of phenotype 3? While these associations may make intuitive sense to a trained physician, intuition is not explanation. Moreover, machine learning models and feature definitions are increasingly designed by data professionals rather than by clinical practitioners alone. Thus, ideally, both clinical and data science subject matter experts should be able to vet the resultant phenotypes to a reasonable degree, considering specialization. There's more information about both this and the clustering techniques in the paper. There are alternative strategies for grouping clinical features without unsupervised learning, aside from standard feature engineering. One prominent example is the Phenotype Knowledge Base, VKB, which offers a crowdsourcing solution to this problem. VKB provides community-generated, pre-validated, and rule-based phenotyping algorithms. While crowdsourcing rule definitions in this way does reduce the burden of curation and validation in some contexts, the database is not comprehensive and may never be applicable to all problems. Moreover, the VKB algorithms may not perform well across data from different healthcare systems. A final strategy is to use established coding systems, and there's more information about that in the paper. The two of interest for us are ICD-9 coding systems and clinical classification software, which the reasons for which will become apparent shortly. In this work, we aim to generate data phenotypes that are interpretable in their formation by disambiguating feature membership. These interpretable phenotypes can then be used to enhance interpretability for other generic ML tasks, for example, additional clustering or supervised learning. We tested 3 ideas. The first was to change the perspective from which we compare similarity and clustering by transposing the input data. Rather than comparing vectors of feature values for each observation, we compared vectors of observation values for each feature. By so doing, the result is an explicit set of features that define the phenotype. It's a simple change, but a less common approach in clustering, and we tested this idea both in k-means and agglomerative clustering. For our second test, we imposed a strict constraint on the results of matrix and tensor factorization, such that features were assigned to only those phenotypes with which they held the strongest associations. The result is an explicit set of features that define the phenotype. And then for both the factorization and clustering methods, we ignored the standard patient association output for reasons that will become clear on the next slide. For each of the 2 proposed methods, we apply data processing technique called one-hot encoding, which translates each categorical variable into a set of binary variables. After generating phenotype groups using one of the 2 methods, clustering and factorization, we treat each phenotype as one new feature in a new model. And then finally, to reassociate the phenotypes with the observations, we calculate an expressivity score, YIJ, for each ith patient and jth phenotype. Since all feature values are binary encoded, we are able to apply the Manhattan distance as a measure of similarity. Manhattan distance is smaller the more similar things are, so thus the expressivity is the complement of the mean similarity for an observation. Using ICD-9 diagnosis and procedure codes as our input features, we tested these methods on data subsets of the well-known MIMIC-3 dataset of ICU encounters from Beth Israel Deaconess Medical Center. The first subset was that of all patients passing through the neonatal ICU. The second was a similar subset of ICU patients ages 65 and above. To compare prediction performance across different methods, we used a simple binary prediction to determine whether the patient's length of ICU stay would be above or below an arbitrary value. We chose arbitrary cutoffs that facilitated simple analysis because our goal was to assess relative performance of the phenotypes and not to solve a specific prediction problem. We were not solving the length of stay problem. More information about the setup can be found in the paper. Our early experiments determined that the inclusion of ICD procedure codes in addition to diagnosis codes had no effect on prediction trends. So the relative performance between differing numbers of phenotypes remained similar whether or not we included procedures. Thus, the remainder of the study focused on evaluation of diagnosis codes only for simplicity. And again, there's more information in the paper. So here we compare prediction ROC scores among the different methods. We used PCA as a baseline technique, and we then compared standard marble and non-negative matrix factorization methods with our 4 proposed methods. We observed asymptotically increasing and converging performance as the data were divided into an increasing number of phenotypes. We then looked at more specific performance metrics at 20 and at 200 phenotypes, since those numbers are roughly comparable to the number of categories in 2 of the most commonly used CCS groupings. For this comparison, we also evaluated models using raw ICD-9 codes and CCS level 2 groupings, since they're commonly used in healthcare. All methods, including the ICD and CCS baselines, had greater accuracy than random sampling. And moreover, most methods yielded similar performance, except for CCS, which was significantly poorer by most metrics. However, interestingly, CCS did provide the greatest precision. Finally, the K-means method had the highest scores by 1% for 2 out of 4 metrics, and was competitive with CCS in terms of its precision. We saw similar performance results with an increasing number of phenotypes, for example, at 200 phenotypes, as you can see here. And again, we observed similar results in the geriatric predictions. There was increasing prediction ROC with an increasing number of phenotypes once again. This was a larger data set in terms of both the number of patients and the number of features, so as expected, that convergence happens at a larger N than in the neonatal results. And finally, we saw comparable performance across methods for the geriatric problem after a sufficiently high number of phenotypes. And as you can see, the standard NMF was the top performer with 1% in terms of accuracy and ROC, but performance across the board was comparable. For some prediction problems, there will be gains in model efficiency by grouping diagnoses as clusters. Clearly, we did not see any gains from this test problem, but since the model performance was roughly the same between ICD and phenotyping approaches for both data sets, we also clearly did not see a performance detriment. In terms of the distribution of features within the phenotypes, we saw that feature membership was similar across most phenotyping methods, which confirmed for us that we were in fact identifying underlying patterns. The exception to this was the phenotypes generated by MARBLE. However, as I mentioned earlier, the MARBLE outputs required an experienced clinician to interpret, and moreover, the computation time required for MARBLE became intractable for the geriatric group. Another way to look at model performance is to compare the relative influence of each feature in making a prediction. In this case, the features will be either the ICD diagnosis codes or the phenotypes. The optimal technique for extracting importance information from models like these is a subject of continued research. However, LIME is one of the most prominent methods currently in use. Here we're looking at the mean feature importance as determined by LIME across all instances from all 10 trials as it relates to correct positive predictions for the ICD-9 model. And these ranks are roughly consistent with both SHAP and XGBoost weights in case you're familiar with feature importance tools. When we compare the relative importance of the top features between the ICD-9 predictions and the phenotype predictions, we can see a number of similarities. For example, 6 out of the top 10 diagnosis codes in the ICD-9 prediction are also present among the top features in the K-means phenotype prediction. This is highlighted by the colored boxes. You can also see that the phenotype model is able to capture additional information over the ICD-9 model. Take the diagnoses in the purple boxes, for example, neonatal bradycardia and primary apnea of the newborn. Bradycardia means that the heart rate is very slow, and primary apnea means the cessation of breathing due to a lack of oxygen. Bradycardia commonly follows apnea, so it's no surprise to see these two diagnoses grouped together in the same phenotype. And to understand that relationship, and to understand that these features are indeed related, is easily accomplished with a quick Google search. Here's an example patient for whom the length of stay was incorrectly predicted by both the ICD-9 model and the K-means phenotype model. It was a single live-born patient born without mention of cesarean section. They were about 35 to 36 weeks of gestational age, which is almost for full term. They needed prophylactic vaccination against hepatitis and observation, in addition to being diagnosed with primary apnea. Both models, both the ICD-9 model and the K-means phenotype model, predicted that this patient would have a length of stay of less than 4 days, when the actual length of stay was closer to 9 days. Looking at the LIME output for the K-means model, we can observe that the model placed significant negative weight on several phenotypes that the patient did not express, with significantly positive weight placed on a phenotype that was only somewhat expressed. Whereas the one fully expressed phenotype containing single live-born, etc., had significant negative weight, which is what resulted in the false negative decision. This indicates some potential bias or weakness of the trained model that could be improved elsewhere, or could be improved later, rather. In summary, the proposed phenotyping framework can be used to reduce dimensionality and improve interpretability at little to no detriment to performance. There are a number of ways that we could improve this work. Most notably, there are a number of other methods which we did not have time to test, for example, deep learning or subspace methods. Moreover, the clustering methods which we use to create our phenotypes create mutually exclusive groups. So-called fuzzy methods may produce a more accurate representation of the reality by allowing, for example, allowing diagnosis codes to be present in more than one phenotype. Additionally, once our unsupervised learning methods are more refined for application on categorical data, we could build upon that to also create phenotypes that use continuous data or even phenotype our phenotypes. On a closing note, I'd like to thank the Mimic and Marble teams for the use of their resources, and finally thank you to you for your attention.